to have a small talk on perfect numbers. So to start with, what is a perfect number? A number is said to be perfect if it is equal to the sum of its proper divisors. Examples of perfect number are 6, 21, 496, and 8128. What if the number deviates from being perfect? If the sum of proper divisors of a number is more than the number itself, we say the number is abundant, and if the sum is less, we say that it is deficient. 12 is an abundant number, while 8 is deficient. Perfect numbers have been studied from a long time. But why? First reason lies in the fact that the numbers have intrigued people always. And the second fact is that the people say that in ancient times, if a person had to peak with a certain object, then and if the person has n objects, then it could only be peak with as if it's a proper divisor. So if the number can be represented as a sum of proper divisors, it was the best possibility. Coming back, the first recorded result lies in Euclid's Elements. In Elements, Euclid writes, if as many numbers as we please, beginning from a unit, be set out continuously in double proportion until the sum of all becomes a prime, and if the sum multiplied into the last makes some number, the product will be perfect. So start from a unit, multiply it by 2, that is its double proportion, further multiply it by 2, so what we'll get is the sum of powers of 2. So whenever the summation is prime, multiply the summation by the last number, that is 2 to the power n minus 1. This product will be perfect. So we'll prove this formally. So the theorem states that if n is equals to 2 to the power r minus 1 into 2 to the power r minus 1 such that 2 to the power r minus 1 is prime, n is perfect. The proof is pretty straightforward because we know that the divisors of n are the powers of 2 plus this prime and then this prime multiplied by all the powers of 2. So summation this, we get this is equals to 2n. Hence, the sum of proper divisors is n because here we have included the number itself. So if we subtract the number itself, the sum of divisors is n. The next result is by Nicomachus. He states 5 statements without proofs. The first statement being that the nth perfect number has n digits. Then all perfect numbers are even. All perfect numbers end in 6 and 8 alternately. Euclid's algorithm to generate perfect numbers will give all perfect numbers. There are infinitely many perfect numbers. The truth of these statements we'll see at the end of the talk and comment. After Nicomachus, many people studied perfect numbers from Fermat, Descartes, Mersenne. And it is also said that many famous theorems in number theory, like the Fermat's little theorem, his last theorem, all stemmed out of his study of perfect numbers. So next, we'll give some definitions to make our further talk smoother. So we'll define a function that is the sum of divisors function. This is a number theoretic function denoted by sigma such that sigma of n is equals to summation of t, where d is all the divisors of n including 1 and n. So clearly sigma of n is equals to 2n for perfect numbers, sigma of n is greater than 2n for abundant numbers, and sigma of n is less than 2n for deficient numbers. Next, we'll see that the sigma holds a very beautiful property known as the multiplicative property, which states that sigma of mn is equals to sigma of m into sigma of n whenever GCD of m and n is 1, that is, they are co-prime. So this proposition is very useful because this proves that if we know the value of sigma for all powers of primes, then we can find the value of sigma for any number n. For proving this proposition, we'll first move from left-hand side to right-hand side. So if d is a divisor of mn, then D can be represented uniquely as a product of a divisor of M and a divisor of N. Hence, every term on the left-hand side will occur exactly once on the right-hand side. Now moving from RHS to LHS. So any number T, which is a product of a divisor of M and a divisor of N, is also a divisor of Mn. So every divisor, that every term that will occur on the right-hand side will also occur on the left-hand side. So this implies equality must hold. Now we'll write the value of sigma for a general number n, and in this we'll use our proposition, that is the multiplicative property of sigma. So first, to prove this, we'll find the value of sigma of m for a power of prime. So if m is a power of prime, then sigma m would be equal to the summation of all the powers of p up to p to the power alpha. So the summation is p to the power alpha plus 1 minus 1 over p minus 1. So now sigma n can be represented as a product of all these for each power p that occurs in n. Next is this lemma. So this is pretty obvious that if a number eta divides n, then sigma of eta would be less than sigma of n. But interestingly, a more strong lemma holds, and that is the following, that is sigma of eta over eta is less than or equal to sigma of n over n. So we'll give two proofs for this. First would be a rigorous proof and second would be somewhat an elegant one. Before proving this, I would like to illustrate the power of this lemma. So this lemma says that if we strike a perfect number, then all its multiples would be abundant and all its factors would be deficient. Also, from this lemma, we can conclude that if once we strike an abundant number, then further going to its multiples would make no sense for our search of perfect numbers. So now coming back to the proof, we'll write n and eta as the powers of primes. And because eta divides n, beta i's are less than or equal to alpha i's. So we can write sigma of n over n to be this product and sigma of eta over eta to be this product. Now observe each term of this product and each term of this product. So we'll see, we know that pi to the power minus of beta I is greater than or equal to pi to the power minus of alpha I, because beta I is less than or equal to alpha I. This implies every term of sigma n over n is greater than or equal to sigma of eta over eta. This implies sigma of n over n is greater than or equal to sigma of eta over eta. Now coming back to the second proof, which states that starting by writing sigma n as the summation of d such that t divides n. Now if a number d divides n, then n by d is an integer which also divides n. So this is equal to, by symmetry, summation of n by d such that t divides n. Now we can pull out n because it is not included in this summation. So sigma of n over n is equal to summation of 1 by d such that t divides n. So from this equation, we can clearly see that if eta divides n, then sigma of eta over eta is less than or equal to sigma of n over n. And equality will hold if and only if eta equals to n. Now we know that for perfect numbers, sigma of n is equals to 2n. This implies sigma of n over n is 2. This implies the summation of 1 by d such that d divides n, because sigma of n over n is equal to summation of 1 by d divides n is equal to 2. Now, while defining sigma, we also included d to be 1 and the number itself. So we'll pull out 1. So this is 1 plus summation of d divides n, 1 by d not equals to 1 is 2. So subtracting 1, we get that sigma of 1 by d not equal to 1 and d divides n is 1. So we can say that every perfect number can break 1 into distinct fractions of the form 1 by a. A would be the divisor of n except 1. Here are some examples. We have written the first 4 famous perfect numbers 6, 28, 496 and 8128 to break 1. Now notice that each perfect number breaks 1 in this way, but perfect numbers will not give all such possibilities of breaking 1. Here are some examples to state this. Now, because we don't know even odd perfect numbers exist or not, so for now we'll focus on even perfect numbers. For even perfect numbers, we have already proved one result, and that is the Euclid's theorem, which states that whenever n is of a certain type, then n is perfect. Now we'll prove a somewhat converse of this, and this is the famous Euclid Euler theorem. It states that if n is an even perfect number, then n has to be of the form stated by Euclid. We'll see 4 different proofs of this theorem. The first one by Euler. So Euler uses the multiplicative property of sigma. He starts by writing n as a power of 2 and an odd number m. Then we can write sigma of n to be equal to sigma of this power of 2 and m. And we also know this is equals to 2n. So equating both of them, we'll see that sigma of m should be divisible by 2 to the power n, because 2 to the power n minus 1 is not divisible by 2. Hence, sigma of m over 2n is an integer. So let sigma m be s, then and sigma of m over 2n be q. Then sigma of m is 2 to the power n into q, and m is 2 to the power n minus 1 into q. Now we divide this into 2 cases. The first case being q equals to 1. So if q equals to 1, then m is equals to 2 to the power n minus 1 into 1, that is 2 to the power n minus 1, and m is equals to 2 to the power n into q, that is 2 to the power n. So this is only possible if 2 to the power n minus 1 is prime. So this gives the form stated by Euclid. Next, we'll consider the case when q is not equals to 1. If q is not equals to 1, then m is equals to 2 to the power n minus 1 into q. And because q is not equal to 1, q is also a factor of m. So sigma of m should be greater than or equal to 1 plus q plus 2 to the power n minus 1 plus the number itself. And this gives that sigma of m is greater than or equal to 2 to the power n into 1 plus q. But we know that sigma of m is 2 to the power n into q. So we get a contradiction. This implies that q not equal to 1 is not possible. So if there exists an even perfect number, then it has to be of the form stated by Euclid. The next proof is by Dixon, which is a similar proof, but is somewhat a clever one. It uses the same property of sigma m, that is the multiplicative property of sigma of m. So similarly, we'll get 2 to the power n into m is equals to 2 to the power n minus 1 into sigma of m. Bringing this to the denominator, sigma of m is equal to 2 to the power n into m divided by 2 to the power n minus 1. Adding and subtracting 1, we'll get this is equal to m plus m over 2 to the power n minus 1. Now, sigma m and m are integers. So m over 2 to the power n minus 1 should also be an integer. So sigma m is equal to m plus m over 2 to the power n minus 1. So this is an integer. Let this integer be d. So sigma of m is equals to m plus d. This is only possible if d equals to 1, because in all other cases, the sigma of m should be equal to m plus d plus m over d plus 1. So the only possibility is d equals to 1, which implies 2 to the power n minus 1 is equal to m, and this is prime. Again, this gives a number of the form stated by Euclid. Next, we'll see the proof stated by McDaniel. This proof uses the lemma that if eta divides n, then sigma of eta over eta is less than or equal to sigma of n over n. So starting from 2 to the power n into m is equal to 2 to the power n minus 1 into sigma m, every divisor of 2 to the power n minus 1 must divide m, because it does not divide 2 to the power n. So let p to the power alpha divides 2 to the power n minus 1. So this p to the power alpha will also divide m. So sigma of m over m would be greater than or equal to sigma of p to the power alpha over p to the power alpha. Expanding this and just considering two terms from the numerator, we'll get sigma of m over m is greater than or equal to 1 plus p over p. Now, we know that sigma n is equals to 2n, so sigma n over 2n is equals to 1. Now, writing this in other form, that is sigma of n is equals to sigma of 2 to the power n minus 1 into sigma of n. And 2n is 2 to the power n into m. Here we'll put the minimum value of sigma of m over m from this equation, that is 1 plus p over p, and this would give us 1 is greater than or equal to 1 plus something, which is positive because p 2 to the power n minus 1 is divisible by p. So this has to be something positive. So the only possibility is that this is 0. So putting this equal to 0, p is equals to 2 to the power n minus 1. So for equality to hold here, sigma of m over m should be exactly equal to 1 plus p over p. And this is possible only if p is equals to 2 to the power n minus 1, that is alpha equals to 1 and m is equal to p. So this again gives us the number of the form stated by Euclid. The last proof, the fourth one, by Nofmaker is the most general proof. He states, let n is equals to 2 to the power alpha 1 into n, and write n as the product of primes. Then sigma n would be equals to sigma of 2 to the power alpha and sigma of each of pi to the power alpha. So that would be the product of from I equals to 2 to k, 1 plus pi plus up to pi to the power alpha. Bringing this to the denominator, we'll get this. Now we also know sigma of n is equals to 2n. Just putting the value of n. Now we know that 2 to the power alpha 1 plus 1 minus 1 does not divide 2. So this implies that this could be written as the product of powers of pi's. Let it be gamma i's. This will give us, just replacing this would give us that 2n over 2 to the power alpha 1 plus 1 minus 1 is equal to 2 to the power alpha 1 plus 1 product of pi to the power alpha I minus gamma I for I equals to 2 to k. Now adding and subtracting 1, we'll get that this is equal to 1 plus product of pi to the power gamma i's for I equals to 2 to k multiplied by I equals to 2 to k pi to the power alpha I minus gamma I. And we also know that this is equal to the summation of 1 up to pi to the power alpha from I equals to 2 to k. Now, so just we equate these two. By equating these two, we'll see that this has just two terms. This implies that all gamma i's have to be 0 except gamma 2. And alpha 2 has to be alpha 2 shall be equal to gamma 2, that is 1, and k equals to 2. Again, this gives us the number of the form stated by Euclid. So by these four proofs, now we know that all even perfect numbers have to be of the form stated by Euclid, that is, n is equal to 2 to the power n minus 1 into 2 to the power n minus 1. Now, this implies whenever we'll strike a prime of this form 2 to the power n minus 1, we can generate a perfect number capital N. So now, finding even perfect numbers is similar to finding Mercian primes. Now of theorem regarding how to find Mercian primes. So this is the theorem by Cattell de Fermat, which states that if 2 to the power n minus 1 is prime, then n itself must be prime. Notice that this is a necessary condition, not sufficient. That is, if n is prime, this does not imply that 2 to the power n minus 1 is prime. So the proof is straightforward. We'll prove this by contradiction. So we'll start that let n is not prime. If n is not prime, then we can write n to be equal to r into s for some integer r in s. This would prove that we can factorize 2 to the power n minus 1. So if we can factorize 2 to the power n minus 1, it cannot be prime. So we get a contradiction. So this implies n must be prime. Next, we'll see some properties of even perfect numbers. Now, why shall we look at the properties of even perfect numbers? Whenever we study something, what we want is that if we can state the definition of that in terms of some bunch of properties. So that is why we look from the properties of certain things. So we'll start by property number 1, which is if n is an even perfect number, then n has to be triangular. Now, if a number m is triangular, then it is the sum of consecutive integers starting from 1. So clearly, m is of the form k into k minus 1 over 2 for some k. Now we know that n is of this form, so multiplying and dividing by 2, we can get that n can be converted to this form of the form of a triangular number for k equals to 2 to the power n. This implies that every even perfect number is also triangular. Next, we'll say that any even perfect number can be written as a sum of cubes of odd numbers. For this, we know that sum of consecutive cubes is n into n plus 1 whole squared by 4. So because we have to find the sum of odd cubes, we'll find the sum of odd cubes by writing sum of 2m consecutive integers and subtracting from that the sum of even powers, even cubes. Solving this, we'll get that the sum of odd cubes is equal to m squared into 2m square minus 1. Now, replacing m to be equal to 2 to the power n minus 1 by 2, and we can do so because we know that 2 to the power n minus 1 is prime, and whenever this is prime, n has to be prime. So any number greater than 2 that is prime is odd, so n minus 1 by 2 is an integer. So when we replace m by 2 to the power n minus 1 by 2, we'll get the number in the form stated by Euclid. So this proves that any even perfect number can be written as the sum of odd cubes. Next proposition is every even perfect number ends in a 6 or 8. Remember that this is a part of assertion mentioned by Nicomachus. Okay, we'll get to that later. First, we'll see the proof. So let n is equals to 2 to the power n minus 1 into 2 to the power n minus 1. That is the form of any even perfect number. And we know n is prime by Cattell-Fermat theorem. Also, we know that any prime greater than 2 is of the form 4m plus 1 or 4m plus 3. So we'll divide into two cases. Case 1, if n is equal to 4m plus 1. Putting that value and taking mod 10, we'll get that whenever n is of the form 4m plus 1, this is congruent to 6 mod 10. Considering the second case, when n is equals to 4m plus 3. In that, we'll get that this is congruent to 8 mod 10. Next, we'll see the property that the iterative sum of the digits of an even perfect number other than 6 is 1. So we'll do this in two parts. First, we'll claim that any even perfect number is congruent to 1 mod 9. So we know that for n to be perfect, n has to be prime. So n is congruent to 1 mod 3 or 2 mod 3. So we'll again divide this into two cases. First one, n being of the form 3k plus 1. Now notice that if k is odd, then n would be even and hence not prime. So k has to be even. So this gives that n is of the form 6s plus 1. So writing n and replacing n to be 6s plus 1, we get that this is congruent to 1 mod 9. Now considering case 2, that is n is equals to 3k plus 2. Here, if k would be even, then n would be even and not prime. Hence, hence k has to be odd. So this gives n to be of the form 6s plus 5. Putting this value and doing this mod 9, we get this is congruent to 1 mod 9. So what we have proved is that any even perfect number is congruent to 1 mod 9. What is left to prove is that the iterative sum of the digits is equivalent to the congruence class mod 9. So to prove that, consider a number n with digits ar up to a1, a0. Then expand this. This would be from ai into 10 to the power I for I equals to 0 to r. Take this mod 9 we'll get that this is equals to summation of I equals to 0 to our AI. So this implies that the summation of the digits is congruent, is same as mod 9. So now, I would like to mention that all these properties are not just true for even perfect numbers. They are true for even a larger class. Like observe the property first, n being triangular. Here we can see that here we have not even used that 2 to the power n minus 1 is prime. We have only used that n is of this form. So we can say that any number n which is of this form is triangular. Considering property 2, what we have used is that n has to be odd. That is, n minus 1 by 2 has to be an integer. So any number of the form stated by Euclid such that n is odd can be written as a sum of cubes. Next, next what we have stated is that it ends in 6 or 8. So for unity digit being 6 or 8, what we have used is that n is not divisible by 2. Again, we have used the same thing, that n is odd. For considering the iterative sum of the digits, we have used that n is not divisible by 3 and not divisible by 2. That is, n is prime, and because we have not used that n is not even used that n is prime. We have only used n to be not divisible by 2 and 3. So any number of this form such that small n is not divisible by 2 and 3 holds this property. So this says that our search for a bunch of properties that are self-contained, that can state that sigma of, if a number n holds these properties, then sigma of that number has to be 2n, is still incomplete. Now, we'll again revisit the assertions made by Nicomacheus and comment on their truth. So, the first assertion that he states is that the nth perfect number has n digits. We have seen that the first 4 perfect numbers are 6, 28, 496, and 8128. And we can see that 6 has 1 digit, 28 has 2 digits, 496 has 3, and 8128 has 4. Hence, this assertion holds for the first 4 perfect numbers. But now, look at the fifth perfect number. The fifth perfect number is 3,355,036. This number has 7 digits. Hence, this assertion breaks at the fifth perfect number, and hence it is false. The next assertion made by Nicomacheus is that all perfect numbers are even. For this assertion, we still don't know if this is true or false, because we don't know if odd numbers exist, odd perfect numbers exist or not. Next, the assertion made by him is all perfect numbers end in 6 and 8 alternately. What we have proved is that all perfect numbers end in 6 and 8. But do they do this alternately? The answer is no. Because the fifth perfect number and the sixth perfect number both end in a 6. So this assertion breaks at the sixth perfect number. The next assertion by him is that the Euclid's algorithm generates all perfect numbers. We have proved by our famous Euclid Euler theorem that Euclid's algorithm generates all even perfect numbers. So this assertion is equivalent to the assertion 2, that is, all perfect numbers are odd. So if all perfect numbers are odd, then Euclid's algorithm will generate them all. The next assertion made by him is that there are infinitely many perfect numbers. For this is an open question. We don't know. Even if we leave odd perfect numbers, we don't know if there are infinitely many even perfect numbers, because we know that searching for even perfect numbers is same as searching primes of the form 2 to the power n minus 1, that is Mercian primes. And what we don't know is that if there exists infinitely many Mercian primes or not. So we can see that assertion 1 and 3 are false, while 2, 4, and 5 are open questions. So it seems that the assertion made by Nicomacheus were just observations which he could drew from the first 4 perfect numbers 8, 21, 496, and 8,128. Next, we'll have a glance at odd perfect numbers. So starting with that, we don't know if such numbers exist or not, but if such numbers exist, then they have to satisfy the following conditions. First being that n is of the form q to the power a into all other powers of prime to be even. Why this? Well, we know that n is odd because we are searching for odd perfect numbers. So all pi's have to be odd. Now we know that if a number n is a alpha power of p, then the summation of the divisors of that number would be even if the power is odd, and it would be odd if the power of the power alpha is even. So we know that for a number n being perfect, n has to be equal to 2n. This implies that the sigma n has to be divisible by 2, but not by 4. This implies that only one of the powers of prime can be odd. All others have to be even. And one has to be odd because it has to be divisible by 2. Next is that n is greater than 1500 power of 10. This is because we have checked all numbers lower than this. The next two conditions are that the n is not divisible by 105 and n has to belong to one of the following three congruent classes. The first one being 1 mod 12 or 117 mod 468 or 81 mod 324. The proofs of these two assertions are somewhat difficult to mention here. I would like to mention here that if there exists some odd perfect number, then it also must hold another beautiful property. That is, if there exists a number n which is odd and is perfect, then that number multiplied by 2 would be a tri-perfect number, which is that the summation, that sigma of that number has to be 3 times the number. So both these two statements are equivalent, and this is a somewhat nice property. So on this note, I would like to end this talk by the following words by Martin Gardner. One would be hard put to find a set of whole numbers with a more fascinating history and more elegant properties by greater depths of history and more totally useless than the perfect numbers. Thank you for listening to me. If you have any questions, then please ask.
Thank you for the wonderful talk. I had just one question. I wanted to ask that what is the current status of the odd perfect numbers? I mean, has there been any considerable progress in the past few years, or is the mathematics world still devoid of any such progress?
We still don't know if they exist or not, but we are just trying to get more and more properties that if such a number exists would satisfy and find some contradiction. So there are a lot of properties that we have found for these
Yes, yes,
powers
yes.
as well. And we have also found that if the number does not include any prime factor of 3, 5, or 7, then it has to have some factors greater than a certain number. And like a lot of properties have been found surrounding this, but none of them have proven either their existence or their non-existence.
I see. Thank you.
Hello,
Yeah.
am I audible?
Yeah.
I would like to ask one question. In the last slide, you can we go back to the yes, this one. You said that the last proposition is difficult to prove, but does the same thing hold for the second last statement that is written here? And
Yeah, it
if
is. It would need some new things to be defined, and like if you are interested, I can send you by mail or something. But it would be a little difficult for me to explain it here.
okay, thank you.
Thank you.
So I don't think we have any more questions, Rishika.
Yeah.
So thank you for the talk. That was a great talk. Please join us again next week for a talk by Soham Bakshi on the set of points of continuity and maximally discontinuous extensions for the same. Thank you.